The overall goal of the following experiment is to demonstrate a new nanoelectric sensing platform for point-of-care biomolecular detection in high ionic strength solutions. This is achieved by operating single-walled carbon nanotube field effect transistors at high frequency to mitigate the ionic screening effect. First, the nanotube transistors are fabricated and functionalized with receptor molecules. As a second step, the devices are encapsulated with a microfluidic flow channel which allows biomolecule sample solutions to be injected for real-time sensing. Next, the single-walled carbon nanotube field transistors are operated as high-frequency mixers in order to overcome an ionic screening effect. At high driving frequency, ions in solutions can no longer screen the nanotube sensor effectively, allowing the oscillating dipole moments of surface-bound biomolecules to be detected. The results show the detection of streptavidin biotin binding in 100 millimolar background solution based on monitoring changes in mixing current at 10 MHz driving frequency.
The main advantage of this technique over existing methods like direct current detection is that it overcomes the Debye screening effect, which fundamentally impedes direct current detection in high ionic strength solutions.
In contrast to traditional charge detection-based sensors, our method detects the dipole moments of biomolecules by exploring the high-frequency response of nanotube transistors.
First, place a photomask with rectangular pits for catalyst onto a photoresist-coated silicon wafer and expose it to a UV irradiance of 300 mJ per centimeter squared for 0.3 seconds.